Good morning. I'm filling in for Professor Hoffman, who is off addressing the French Parliament at this moment, or maybe it was yesterday afternoon.
Tough choices whether to stay here.
Well, that's right, Noah. These days, the issue of knowing where you are, navigation, is really taken for granted. We have GPS in our cell phones, GPS in handheld devices. GPS tells the taxi driver whether or not he should be turning up that one-way street. When we began with human space travel, particularly as we entered the Apollo era, the question of navigation along with guidance and control was still a major issue, and in fact, it was rather uncertain whether or not in the Apollo mission we're going to be able to with assurance, do all of the navigation required for the going to lunar trajectory and then doing the precise navigation to land on the moon. And with great confidence, Stark Draper and his associates in what was then the instrumentation laboratory, now the Draper Laboratory, assured the new NASA that it could be done, and it could be done precisely and on schedule. And darn if they didn't do it. The history of leading guidance, navigation, and control has now, for a period of over half a century, been located just adjacent to, at one time, part of MIT. In the instrumentation laboratory, now Draper Laboratory, and the tradition carried on through Apollo to the space shuttle program, and then as you were aware, beyond that into NASA's current plans. We're privileged today to have discussed with us the guidance, navigation, and control issues on the shuttle. Dr. Phil Haddis. Dr. Haddis, a graduate of Northwestern and Caltech, and with his PhD from the Aeroastro department at MIT, has been employed at Draper since 1974. He is a member of the laboratory technical staff, which is the highest technical position available there. He serves as the technical lead for the Crew Exploration Vehicle Development Program in GNC at Draper Laboratories. Phil has been very active in AIAA. He's a fellow. He's been head of the New England region and has received the Draper Lab Distinguished Performance Awards and various NASA recognition awards for his contributions to STS-1 and STS-8 missions, and we'll hear about Draper's contributions and the overall issue of GNC.
Thanks a lot, Larry. I should just point out, when I came up here as a graduate student to pursue my doctorate, I was a Draper Fellow. I started working on the shuttle as a Draper Fellow, so much of the work I'll be talking about here, I was probably only a year or two older than any of you when I was doing this. That's turned out to be fairly useful to NASA because with the shuttle still flying, from time to time issues come up and they still pick my brain about what we did in 1974, 75, and 76, which wouldn't have been so easy if I'd been my current age then. But it's also a little bit alarming because it means the people that are working on the system now don't really understand why it was designed the way it is. Now, the other thing they could have asked me for was the report on which this material is based, which I wrote in 1983 to educate the rest of the people at Draper who were going to work on the program subsequently about this system. Now, the other thing I just want to say, and feel free to interrupt me at any point to ask questions. I'm going to be covering a lot of ground, and I may not get back to the area that you're interested in asking me about if you wait. So just raise your hand or speak up or whatever you feel like. And the other thing I want to point out is that two things. One, what you're going to be looking at was largely what was done for the first shuttle flight, except where I mentioned specific upgrades. Now, I'm not going to be comprehensively covering all the upgrades that have been done to the shuttle since. What you will also note is this presentation will be largely monochrome. And why? Because it's drawn from a presentation in 1983 when there was no such thing as a laptop or PowerPoint, and color was a real pain to get. You had to go to the artist and then get it lithographically reproduced, which was incredibly costly. What color you see, I've added now, and it's limited, except for a couple pictures at the end. I do have some before and after cockpit pictures at the end. So you'll periodically see a chart like this, topics of discussion as we go from section to section, where I'm going to delineate the areas I'm going to cover. So there's going to be a whole bunch of sub-bullets for each of these areas as I go through. This will be not real deep unless you ask me the questions. I'll go as deep as you want with the questions, but covering a lot of ground. Some of these pictures you may have seen in one form or another, but I should just highlight certain points. The systems that related to the flight control were placed all over the shuttle. In the forward area, which was the only pressurized portion of the shuttle, below the livable area was the avionics bay. And in there were the computers, the inertial measurement unit, and I want to say something about that in a moment. What they refer to as multiplexers, demultiplexers. You had a lot of analog systems, or you had to convert back and forth between digital and analog. And the electronic boxes that drove the commands for the reaction control system thrusters. And then you have hand controllers and displays and indicators in the cockpit. In the back, you have pods, which had the many of the reaction control system jets and the orbital maneuvering system thrusters. And I'll be talking quite a bit more about them later. And there was also an aft avionics bay that had specific subsystems that were deemed, for which it was deemed unacceptable to have them forward. Some of them were local analog digital conversion boxes, but also rate gyros, which were used during ascent and entry, where they wanted them closer to the center of mass by being in the back than in the front, and avoiding some of the flexure issues associated with the long distance to the front. This particular configuration you're looking at is after before the external tank separated, after these solid rocket boosters had come off. This configuration is where the story begins, because what I'm going to be talking about is the part that Draper did, which is the exo-atmospheric flight control system. And that begins at main engine shutdown and ends when you hit 400,000 feet on the way back. There are different phases that we'll be talking about. The first is what we refer to as insertion, which is from the time the main engine's cut off to the time you do initial orbit circularization. And that includes a brief but design challenge phase while you're attached to the external tank. It includes the separation maneuver from that. And in the original flight profile for the shuttle, 2 burns of the orbital maneuvering system. The original orbit insertion strategy for the shuttle put it in an orbit that was typically had an apogee of about 60 nautical miles, a perigee of just a few nautical miles. What you would do is the first burn would raise that perigee up to the 100-plus nautical mile target altitude, and then the second burn halfway around the Earth would put you into a circular orbit, and then you would begin your mission there. Later in the program, for overall efficiency, in order to improve the payload margins, that strategy changed, and they tended to do more what they called direct insertion, which had a substantially higher apogee. The perigee wasn't much higher, but you would end up somewhere between those two, and then you would do 1 ohms burn, and you get a net gain of maybe 1,000 or 2,000 pounds, which became very important. During this insertion phase, all the applicable sensors were on. Now, I said I was going to say something about the IMU, and you see rate gyros. Most of you don't even think probably these days about having rate gyros separate from an inertial measurement unit. You get these combined packages called inertial navigation systems now. They're actually navigators that got the software that do all the processing for you. They even have built-in GPS receivers. Of course, we didn't have GPS then. The inertial measurement unit was a pretty clunky gimbaled device at the time the shuttle first flew. It subsequently got upgraded to ring laser gyro systems. But that inertial measurement unit was simply outputting angles. There were significant throughput issues because you had to do a lot of data crunching to get rates from that. Computers are really slow. I'll talk a little bit more about that in a few minutes. So having rate gyros separate was a way to get data that these days would be all built into one box. General purpose computers, there were all of them were on during ascent. I'll talk about the partition of them, but there were actually 5 of them. And the Vernier reaction control system, which is a small group of jets, and I'll point those out later, were not active. The larger thrusters were. And then after the second ohms burn, you transition to another flight phase. And why all these flight phases I'll get to in a couple minutes also. That orbit phase began after that second burn. You quickly open the doors so that you could dump waste heat. The radiators are on the inside of the doors, and when the doors are closed, the heat just radiates back into the vehicle. All payload operations are during this phase, and you did a lot of power down to save. You're working off of fuel cells, limits your mission life, both because of the limits on the weight of the reactants and on the places you can put any extra tanks. So you turn off the rate gyros, you don't need those anymore, and I'll explain why. 2 of the 5 general purpose computers were shut down. This also being late 70s computer design, you're talking maybe on the order of a couple hundred watts per computer, which, by the way, I'll explain more, but it was a 104,000 word memory capacity. That was actually an improvement from the approach and landing test when it was 64,000 words. And then you turned off 2 of the 3 redundant inertial measurement units except for critical phases. Also to save power, the feeling was that if you lost your navigation reference, you had a relatively benign environment to bring one of the others up. And the vernier thrusters were made available because they were used for fine control. Then you have the deorbit phase. You close the doors again, you do the deorbit burn. You dump any residual propellant from the forward tanks by simultaneously burning opposing thrusters in order to get an acceptable center of mass for entry, which is getting the acceptable location of the center of mass for attitude and thermal control during entry is very critical. You reactivate all the sensors. You go back to all the computers being up. You turn the vernier jets back off, and you fly the vehicle using this mode until you hit 400,000 feet, which is about where you pick up 0.05 Gs, and that's where the entry phase takes over. And this is just a summary of the profile. Now, this is where I wanted to take the opportunity to talk a little bit about computers and profiles and everything else. When we started this program with a 64,000 word computer, I talk in terms of words instead of bytes. The architecture of this computer didn't have bytes. You had words and half words. Each word was equivalent to about 4 bytes in terms of number of characters you could insert into it, but you only could break it down in pieces of 2. So we had 208,000, well, 1,020 times 1,024 pieces of memory that we could work with on this computer. For the approach and landing test, which was very limited, you flew it off of a 747 for a couple minutes. 64,000 words just worked just fine. And they were chugging along with the program saying we're going to get all this orbital mission stuff into that computer. And of course, we discovered probably a year after we really began the job, we began the job seriously in 75, and by 76 it was obvious 64,000 words wasn't going to work. They upped it to 104,000 words, and it was probably obvious 4 months later that 104,000 words wasn't going to work. So the solution, in addition to de-scoping as much as possible what you had to have, was to separate the computer loads that you had for up and down from what you did when you were doing your orbital mission. And then you had something called a mass memory device, which was basically a tape drive, which when you went from this phase to this phase would reload some of the computers, and when you went from this phase to this phase would reload them again. And I said there were 5 of these computers. 4 of them were what I'll be talking about. It was the primary computer set, quad redundant, so that they would vote, data going in and out, all data going in and out to decide whether or not there was an inconsistency between one computer and the others, and it would automatically deselect a bad computer, the implications of which I'll talk about probably about 3/4 of the way through the presentation. So when you went up and down, all 4 computers were operating the same software. The 5th computer was called the backup flight control system, and the reason it was there, these 4 primary computers, a chunk of that 104,000 words, probably 30 to 40,000 words, was used to assure the computer set operated successfully redundantly. there was always a concern that there would be a generic software error that would show up at some bizarre time, and you could pull down the whole computer set. So there was an independently coded, similarly architected from the standpoint of algorithm content, but independently coded software called the Backup Flight Control System, that on the hand controller there was a button the crew could hit that panic button if they needed to, and the system would revert from the primary system to backup system. Never happened in the history of the program. It's never been used, but it's still there. And so those 5 computers are all operating on the way up and on the way down. Now, when you go to the on-orbit phase and only 3 computers are up, you freeze dry, as they say, to the computers. One computer remains the backup flight computer, turned off, ready to turn on for an emergency entry of the backup. The other one is a primary software load, ready to start. The remaining 3 computers, 2 of them were redundant set for the on-orbit functions. And one of them, again, because of memory problems, everything payload related was in a system management and monitoring other non-flight control related functions went into other computers. So they did this spread of functions across computers in addition to adding a tape drive in order to accommodate the memory constraints, because the shuttle mission was so much more complex than what the computers were originally designed to accommodate.
Phil, you say it never happened. Have there been instances in which any of the backup computers have been brought online?
Okay, there have been instances in which primary computers have failed.
Yes.
There's never been an instance in which they've reverted to the backup system. Now, when the primary systems fail, and I'll elaborate this in more detail, there are while each computer computes the functionality for everything, they only controlled more or less a quarter of the subsystems. And there's a distribution that some of the charts toward the end will talk about how that's done, and there's implications associated with what you lose when a computer goes down. But if you have time and you're in a non-critical flight phase, you can restring those things to the remaining healthy computers and recover access to those systems even though that computer's gone down. Now on STS-9...
That was, incidentally, our MIT department's first shuttle flight.
That was the...
and it had Byron Lichtenberg, one of our people.
It turned out what happened to be floating solder balls in an early version of these computers that caused intermittent shorts. And one computer went down before entry. They recovered the string. Another computer went down during entry. And because they had reconfigured the string, they had 3 of the 4 strings left, but only 2 computers. And another one failed on touchdown. And had that one failed before touchdown, they probably would have reverted to the backup system. That's the closest they ever came to the backup system. Now, the question that comes to my mind there is, since the generic failure was not software, but floating solder balls, which all the computers were susceptible to, what would have happened if they'd gone to the backup system? Because it could have gone down too, and then they would have had nothing. Because the remaining primary computer, once they've gone to the backup, it is not easy to revert in a critical flight phase to the primary system.
Lichtenberg, as I mentioned, was a crew member from our lab. Later, I asked him, how did you feel when the first computer went down and then the second computer went down? Byron was an aero-astro PhD and pretty savvy. He said, well, he was pretty worried until he looked at the commander, who was John Young, and John said, well, we might as well go to sleep because we're not going to re-enter today. And when John went to sleep, he said, well, you might as well go to sleep too, and it'll be all right. And it was.
Yes?
Was the backup computer manufactured by the same subcontractor as the primary?
The computer was the same. The software was not. The computers themselves are all interchangeable AP101 computers. Subsequently, they were changed to AP101S computers, which is a modified version that was used on the B-1 bomber, and they went to 256,000 words of memory, and that's the current state of the art. You have to understand several things. One, it's very expensive to upgrade systems that are already flying. But independent of that, you never fly in space something that's close to the state of the art, because you have to go through all the qualification, which takes a lot of time, and it has to be radiation hardened when you're in space. And when it's a human vehicle, it's also got to go through human qualification. The space station architecture is IBM 386 processor quality. So it's basically like maybe about 1986, 87 early laptop generation computers.
Did they lose an IMU ever? You know, lost an IMU?
Yeah, oh yes, yes. There's quite a few missions where one IMU went down. I don't think there's ever been any missions where they lost two. The IMU failures don't seem to have been anything systemic, but just sort of a random problem. And I'm not sure, since they've gone to the ring laser gyro systems, that they have had any failures. I think it was the mechanical ones from the early days that they had some problems. Now, major requirements for the systems, we had two different autopilots with three phases: transition, which incorporated both the insertion and deorbit features, and on orbit. So we only had two different software loads on that tape drive for the primary flight control system. The rules for shuttle were that after any subsystem failure, you had the capability to remain operational. No critical functions were lost. After two failures, safe operation. All critical things necessary to terminate and the mission and bring them home would be possible, but some of the mission objectives may not be achievable. The system was mainly aimed at controlling rigid body characteristics and velocity changes within specification. Only when we started to look at docking with the Mir and the space station did we start worrying about flexible body effects, and it was because of what they were attaching to and not because of the shuttle, all those appendages and those things. The shuttle does control space station and did control Mir when it was docked, and so there have been some modes, which I won't really be talking about today, but were created to facilitate that control without causing unacceptable loads on those flexible appendages of the stations. And 80 millisecond depth cycle. Two reasons that happened. We originally planned to do 40 milliseconds. The approach and landing test program was. First is less processor burden if you do it half as often. And the other, when it came to the reaction control system, is we discovered in about early 1980, a little more than a year before the first flight, that there was a water hammer effect in the propellant lines on the RCS jets, where the opening the valves caused an expansion wave, which reflected as a compression wave. The closing of the valves caused a compression wave. The intersection of compression waves, if the valves were open and closed too quickly, could cause a catastrophically large compression wave that could burst the line. So they deemed it better, rather than redesign the entire feed system, to limit us to never firing faster than 80 millisecond cycles. Now, that different from Apollo. Apollo had 100 millisecond cycle time, but they had the ability to interrupt the cycle to turn on and off jets if they wanted a short firing. We couldn't do that because of the water hammer effect. We also, because of the propellant feed system, involved a liquid in the tank with zero-G acquisition devices around the surface of the tank, directly exposed to the pressure in helium, which means some of the helium dissolved into the fluid. If the fluid was drawn too fast, the helium could bubble out, causing a gap in those zero-G acquisition devices around the tank, preventing flow. If you get unbalanced flow of hypergolic propulsion systems, you can also get an explosion. So the solution to that was limiting how many jets you could fire at one time off of one tank.
Does everybody understand what the zero-G acquisition problem is?
It's a surface tension based, you have various types of rings and shapes of on there which captured fluid by surface tension to there, which would begin to draw the fluid, and once you began to get some flow because they're firing things, would pull the blobs of fluid into the tanks and into the feed lines from the tanks.
Recall, the origin of the problem is that the fluid will not be at the bottom of the tank. So you risk drawing a bubble.
The surface tension holds enough there to start the firing. When you fire, you get some force. The force draws the blob to the same parts of the tanks where you can acquire the fluid. And as long as you don't draw too fast, the communication between that part of the tank and the fluid remains. This was a very complicated qualification program. A lot of C-135 parabolic trajectory time got used to test out various perturbations of the inside of the tanks. Now, I'm not going to talk about that in detail, but I'm sure there's a lot of papers out in the literature about how they qualified these tanks. I don't think there's too many systems before the shuttle that actually did it this way. Most of them used one-use systems tended to use membranes where you had the pressure on one side, the fluid on the other side, and the membrane would just force the fluid to stay in contact. But the problem is the membranes would degrade over time on exposure to these hypergolic propellants. Hydrazine and nitrogen tetroxide are very chemical reactive materials. For a system that was supposed to be used over many years, up to 100 times, the idea that you'd have to periodically keep opening up these tanks to change the membrane was not attractive when you considered the tanks are deep inside of the structure. So this may have been a unique issue because of a reusable system, but it also may be relevant to systems that, even if they're not reusable, have to have a very long life in space. Modes and submodes I quickly go through, but you had rotation and translation modes. These modes could be used simultaneously for the RCS system and then separately for the OMS system. You had special modes which to get extra oomph out of the RCS jets if you had an abort. That would sometimes be done if the OMS engines weren't available. The OMS engines, there were two of them, which were up on the back right and left pods from that picture I showed a few minutes ago. And you could use one or two depending on what you were doing. And in the RCS rotation modes, you had various ways you could use it. Proportional meant you move the stick, the response you get is in proportion to what you do, how long the jets fire. Discrete means you move the stick and you get a specific amount of rate change. Pulse means you just get a single little pulse out. And acceleration means as long as you're holding the stick out, it keeps firing them. And those are all, there were push button displays that the crew could adjust those. And then there were sub-modes for each of those, which affected how many jets fired, whether or not you wanted to force it to use something that approximated couples, or you were in propellant conservation mode and you're willing to accept getting a rotation rate, which coupled in the translation, you care about that effect. And in the translation, there were various sub-modes as well. And in particular, you would use more jets when you were separating from the external tank to get away as fast as possible. Yes?
For those, on the previous slide, like different pilot or the different modes for the RCS jets, was there one that they happened to use the most, or that was like supposed to be the primary usage, or are they all part of the normal operating?
I think you would rarely use this or this. I think these two were commonly used. This is very fuel inefficient, would only be used as kind of an emergency measure.
That's also very difficult from the point of view of the pilot to have a direct acceleration control.
Right. I mean, this might be something you would call upon if you actually got, for some reason, the vehicle started to spin up unexpectedly, and you would have to neutralize that. Does that adequately answer your question for now? I will.
That's fine.
There'll be opportunity to look a little more detail on that later. But again, you wanted to get off the tank quickly, so you'd use all the jets you had to get off of it. You wouldn't do that later. You would have more jets you would use for roll control while you're on the tank because you had a much higher roll inertia. You wanted to only spend a few seconds on the tank after the main engine shut down. You could often be left with residual rates you had to quickly kill. There was an inhibit on the separation if you had more than half a degree per second in each of the axes. There was actually a phenomena on the first shuttle flight which almost got us in trouble. One of the first things that happens after the main engine shut down is you slew the engines back to a stow position where you want the engines for entry. The reason is the auxiliary power units are needed to move the main engines. You want to shut those down and save the hydrazine for those until you get back to just before entry. On the first shuttle flight, they kicked those engines at about 1 hertz. It turned out the first fundamental mode of the rock mode of the orbiter on the external tank had a subharmonic of about almost exactly 1/4 of that slew rate on the main engines. The slewing of the engines then caused the rocking mode to be excited. We were seeing oscillations very close to the inhibit for the separation. The crew was getting a little worried, but we just caught it in bounds in the automatic mode, and if they hadn't separated in time, it would have gotten pretty complicated to do it manually. They made quite a few changes after that. There were a lot of things we learned in the first flight. I'll point a few of them out as we go along. There was also a launch pad phenomenology. It's not part of my talk, but has this come up in the class about the shock wave from the SRB ignition?
Yes.
Okay. They didn't have those water beds in there on the first flight. And what was relevant here, one of the things that you may or not know is that the struts that hold the forward RCS tanks on the first flight were buckled almost to failure. That wasn't realized till they got home, but had they failed, they probably would have burst and blown up the vehicle. On orbit modes, we have both primary and vernier jets, which we would only used separately except under special circumstances, which were designed substantially after the first flight. We have local vertical and inertial frame of reference control capability with respect to the discrete rate mode. And otherwise, it's pretty similar to what you saw in the previous picture. And submodes, some features were added because of rendezvous. You could do fire a lot of jets on the forward side. If you wanted to do a rapid braking, you could inhibit all the jets that fire in that direction. If you wanted to limit the use of plumes, it turns out that you didn't lose completely your translation control authority when you did that, because the jets in the front and back that were oriented in the x-axis coupled about 20% of their thrust into the z-axis. So if you fired them simultaneously in both directions, you could avoid pluming an object in front of you and still get enough translation to control that axis. And just to show how everything was hooked up, the inertial measurement units and rate gyros and hand controllers and panel controls all went in through these multiplexer devices, feeding the signals then into the computer and displays. And then you had outputs going through these similar type of electronic boxes specific to the reaction control jets that generated the commands that were needed by the solenoid valves that actually opened and closed the hypergolic feed lights. Looking at the whole top-level architecture then of the GN&C system is all those boxes feeding into what was inside of the computer. And inside the computer you had subsystem operation software managing each of the subsystems, doing the redundancy management, the specific guidance navigation control algorithms. There was a moding and sequencing function which was based on both manual and automatic scripts. Then the actual driving of the displays and controls interacted with the flight control system both ways, providing feedback to the crew members and accepting their inputs. And then what was left of the system management function on this computer that didn't go into the separate computer. By the way, anything related to robotic arm operations were operated through that separate computer. One of the issues that came along later in the program is the flight control computer never knew what was happening with the arm. If you take a space telescope-sized payload and put it 40 feet out there, it drastically changes the mass properties. And one of the features you'll see a little later that we stuck in was the ability to, for the crew by push button, to select different tables about expected accelerations of the jets, because we didn't know when we needed to respond to that. There were also flexure issues with the arm, which came up as they went along too, and established constraints on how we operated.
But there was no thought. Was there any thought given to having an adaptive system which would identify the current parameters?
That would have gone way beyond the capacity of the computers that we had. It would be relatively easy to do with the programs we have, but it would never fit in a 104K memory computer. But there's been lots of work that some of my graduate students have done over the years of how we should have done that. Brent Appleby actually, who's now a division leader at the lab, actually did some work back in the 80s. I think that may have been his master's thesis on some of those issues.
It's an opportunity for the student so that there is an infinite memory.
Right, but we're approaching, in reality, we're approaching very large memories, which would allow you to do it.
Well, we go into CEV, we're probably going to assume that 100 megabytes is no big deal for, you know.
The Hubble robotic unfortunately was cancelled, but we were doing exactly that. We knew exactly the position on the arm during all the movement when we were grappling, and we were changing all the tables based on the current angles and the expected inertias and stuff like that.
It's a real challenge to maintain stability in a system where you have no insight into that. But you would never build a spacecraft that way today. So I'm not sure. The challenges we had were very interesting, but probably no longer relevant. The challenges that remain are the flexural dynamic interaction problems. I just wanted to indicate that within the control laws, you have a steering processor. I'll talk a little bit about more, an RCS jet processor, a state estimator, and an OMS processor. State estimator is unique to the on-orbit flight, and you'll see more that represents that in a minute. So I'm going to now, having ended the overview, go into each of the subsystems in more detail, but pulling up this picture to talk about a little more. Get these subsystems in the context. The forward RCS system had 14 primary 870-pound jets and 2 Vernier 24-pound jets. There were 24 and 4 respectively. Those systems are back evenly divided left and right. Each of the pods in the back had 1 OMS engine. The forward RCS system had its own self-contained hypergolic tanks. The aft system had RCS tanks and OMS tanks, which could be interconnected from within the pod or could be cross-fed across the pods. Now, the consequence of flight control system are there are different constraints on simultaneous jet firings, and where you count, how you count it, whether it was only left or right or both, depending on which mode you're in, but allowed, if you had a mission that needed a lot of RCS propellant and you had spare space in the OMS tanks, it allowed benefiting from that.
Why are there so many thrusters pointing in the same direction? For redundancy?
Yes. Redundancy and maximum control authority. You wanted fine control authority normally with redundancy, but for external tank separation, you wanted high acceleration one direction. For rendezvous braking, you wanted high acceleration in the other direction, the plus or minus Z. And for backup to the OMS engine, you wanted to have higher acceleration in the plus X direction. And then when you were doing entry, which I'm not talking about today, but you had an on-demand RCS control authority in the upper atmosphere during hypersonic flight, and you would turn on 1, 2, 3, or 4 yaw thrusters in particular as needed. I think 1, 2, and occasionally 3 thrusters have been turned on during disturbances. One of the things we've learned from the telemetry of the Columbia accident is as the vehicle was falling apart for probably 20 or 30 seconds, the vehicle was controlling very nicely because they kept turning on more and more jets. They were getting major torque imbalances from missing pieces of the vehicle, but it was still controlling the attitude until the damage got so severe that was no longer possible. Again, I already talked about the number of the thrusters. The primary thrusters, for the reasons we talked about, there were many jets, and also because translation and rotation control was accommodated by these. The Verniers, until feature I'll mention briefly later, was only a rotation control system and fundamentally does not have redundancy. I already talked about the on-time. These are just typical propellant loads and thrust levels and specific impulse numbers. You notice that large maneuvers are always a little more efficiently done with the primary jets and even more efficiently still with the OMS, as you'll see in another chart. Life for duty cycles and on time are relevant for a vehicle that's going to fly a lot of missions. So fine control almost always be done with the Vernier jets, not just because of propellant, which it is much more efficient, but also because you'll get a lot more mission life out of it. This is a stick drawing of those. There's a numbering system associated with it. FRL for which pod it's in, up, down, forward, right, left, the last character for which direction it fires, And then the middle number is a manifold. If you see a 5, that's the vernier jets. 1, 2, or 3, or 4. Any jet in a pod that's got the same middle number is on one manifold. If a failure shut that manifold, or a string took down that manifold, all of those jets were lost. When you lose a string, you would have one manifold per pod that you would lose. That means under some circumstances, because the vernier system is redundant, a single failure could take that out, but that wasn't critical to carrying out most mission objectives or to safety. That's probably enough said on that. The ohms, typical propellant loads mentioned here, on time, never less than 2 seconds, so never less than, with one engine, 12,000 pound-seconds impulse with a 6,000 pound thrust, not suitable for fine maneuvers. The RCS jets would always be used to trim out any large ohms burn errors. Had a significantly higher specific impulse, so for large maneuvers you're clearly better off from a propellant weight perspective using that system. Each of the engines had redundant gimbal control, redundant by having one mechanical screw system, but you could drive the nut or you could drive the screw, and there were different electrical systems that did that. This was the maximum authority, and the two axes that each engine could move, a portion of which was used to track the center of mass as the vehicle consumed propellant or delivered payloads, and a portion of which was for actual thrust vector control management. We also had to subtract a little bit. You never want to go too close to hard stops because you risk mechanical failure by doing that. And you always have a little bit of mechanical uncertainty of exactly where you are anyway. So a portion of that was a mechanical uncertainty, and a portion of that was just a mechanical safety margin. Just a drawing in the two different planes of the rotation of the engines, showing the span between the center of, so about 15 feet apart, no surprise given the general cross-section of the shuttle. Important thing to notice is that the engine, while it can point through the CG, is not pointing anywhere near the body axis of the vehicle. And by the way, the vehicle body axes weren't, there was a significant offset between the principal axes of the vehicle and the body axis. The XZ component of inertia in the body axis was quite large. Three units, even with the replacements they've gone through over the years, there remains 3 units for the INSs now, but the IMUs were mechanical systems with quanta for knowledge of state, which were not all that small. And the RGAs were even worse, rate gyros. These quanta were quite significant. The reason was we had a half word in that multiplexer demultiplexer for translating the analog signal to digital signal, which determined based on the maximum range being dictated by maneuver rates were possible during ascent and entry and not on orbit, but we were stuck with that. It was hardwired into the cards. And so we ended up, these quanta then, we discovered there was a 1 sigma probability of every third cycle, 1 quanta noise spike on the data that came across the MDMs. And that was pretty significant when we were trying to do fine control during the transition phase. So that became a...
Were the noise levels determined by this quantization, in effect the AD conversion?
The quantization, the noise phenomenology was related to the electronics of the card, but it was directly related to the least significant bit. So, yes.
The mechanical sensors themselves were superior to that?
Yes, they were. It was the MDM card that introduced the noise.
So if you had used one word from the MDMs, that would have
given the state of the art to have processed that much information across the MDMs would have made it too slow. We're talking orders of magnitude slower electronics from the late 70s than you have today. So the half word was dictated by the data rates that we required of these boxes. So now I'm going to go into specific features in the software side. Yeah.
With the gyros, how often do they have to be replaced? Because it seems on Hubble and Station, for example, where we always hear bad news of the gyros have to be replaced every so often.
Well, these are, okay. First of all, what I'm talking about here at the time the shuttle first flew were mechanical gyros. Hubble may have started mechanical gyros. They've been changed out at least once or twice, are probably fiber optic systems. Hubble has the problem that it's in a fairly high orbit, 300 plus nautical miles high for the shuttle anyway, has a significant radiation exposure, particularly when it goes through the South Atlantic anomaly of the radiation belts, which at 300 nautical miles is much more time they spend in that than at 100 nautical miles. Cumulative radiation damage to the electronics in those gyros is probably a contributing factor to the failure rates that they're seeing on Hubble. These are, I would say they must spend a few % of their time in the South Atlantic anomaly at that altitude.
Are the gyro replacements, we're talking about measurement gyros or attitude control gyros?
Well, the fine guidance gyros are the ones that have been the big problem on the Hubble. We're talking a different qualitatively different regime we're operating here. The quantization, take away the noise effects, was something we could live with for operating the flight control system. In Hubble, you want to be able to measure rates 2-3 orders of magnitude lower than what we're talking about here. So the actual design of the sensor is substantially different because they're trying to get very, very tiny little rates out. These are trying to maintain the image lock when you're using the full magnification capability of the telescope on whatever target that it has. Nevertheless, I would imagine that if the shuttle gyros are staying at 300 nautical miles for 5 to 10 years, they would fail too. Radiation is one of the fundamental drivers for all missions, and the South Atlantic anomaly is one of the big drivers for low inclination. Space telescopes are 28.5 degree inclination, so they don't have to deal with the magnetic fields coming in toward the poles, which a polar mission has to, but there is this big dip in the Van Allen belts off the coast of South America, which poses a problem for everything that is in low orbit. The functionality we have in the autopilot, we use the rate gyros and the inertial measurement unit and the transition DAP to get states directly, giving us attitude, giving us rate. On orbit, we have the gyro shut down to conserve power, IMU data only. That then dictates that we are going to have a state estimator on orbit. We have to put some special features to overcome the rate gyro noise in the transition phase, which isn't relevant when the rate gyros aren't operating in the on-orbit phase. We have the vernier jets and the associated algorithm logic for on-orbit, which isn't in the transition phase. We worry a lot more about every detail of propellant deficiency on orbit because we spend so much more time there. So we have a lot of features we've added to minimize propellant there. The ohms capability in the two phases is actually identical, with both of them having a capability to wrap around the RCS jets to the thrust vector control should the thrust vector control not behave properly during an ohms burn. And then this just delineates the various features you have for steering, ohms and RCS, where we add lots more features because there's lots more things you are attempting to track when you're doing your mission on orbit than when you're just trying to get to and from orbit. Notice the rates that we're talking about. Typically, you look at an INS box these days and we see hundreds of hertz data rates. What restricted us here was how fast could we crunch this. None of the software was in the sensor package. It was in our computer. And we had a severe throughput problem. And the solution, since we had the rate gyros for rates, and we only needed the IMUs for attitudes, and the rates could be used to extrapolate attitudes for a reasonable period of time, was to greatly reduce the processing rate of the IMU down to on the order of 1 hertz. Submultiple of 25 hertz, which is why it's 1.04. On orbit, since it was our only source of information, we had to eat a larger processing burden, operating them at 6 1/4 hertz, but we still were extrapolating in between the state estimator, is a very long time constant. We'll talk a little bit about what we're doing with that, but everything down here is operating 12.5, and we're getting the data in at 6 1/4. So there's a lot of things you would do differently simply because you don't have these low rate constraints due to throughput limits. The architecture then for the autopilot, this being representative on orbit, is you would have a maneuver module where all the features for steering the vehicle would be, kind of an adjunct to guidance. You would have these modes controlled by the crew and the push-button display of what the stick deflections would do. You would have the phase plane, which would be tracking attitude error, rate error, and whether or not you should fire jets as a function of those errors, separate per axis. Everybody know, are there people here that don't know about phase planes? Is that a, okay, well, the concept of the phase plane, you go to optimal control theory and you look into a situation where you have a control effector which is on or off bidirectional, which is what thrusters are, and you look at what it takes, given an error in a plane which is attitude error and rate error, and you want to get minimum time to neutralize that error to 0, it turns out that a parabolic trajectory will be the optimal control solution. It turns out that it is also fuel optimal, even though it's easier to solve the problem from the time optimal point of view. But of course, you have uncertainty in your knowledge, quantization in the jet firings, minimum impulse bits and all. So you see parabolic pieces of surfaces here, but you have lots of dead zones I'll talk a lot about more to assure that you don't inefficiently use the jets, that you aren't constantly trying to fire the jets to get exactly to the origin, which is never possible. The state estimator, which is a form of a Kalman filter, and then the jet selection logic, which is essentially for the primary jets lookup tables, but turn out to probably be the first use of rule-based intelligence to precede getting. We didn't think about these things in that time, and when I talk about the stringing later, I think we were also using an early version of failure tree analysis, but in the 1970s, none of these things were named. And then you have various loads for the parameters that determine these dead zones and tables and all, and the crew would select these from push-button displays. For the ohms, you could either have hand controller inputs or cross-product steering and based guidance inputs, which would then go into roll and pitch and yaw, thrust vector processing channels where roll and pitch were coupled. Roll is only possible, of course, when you're firing 2 engines by differentially pitching the gimbals on the 2 engines. This would actually be an RCS loop automatically with 1 engine, but you had to have the 2 paths coupled when you were trying to do both of them, but the yaw axis was separate. Just keeping an eye on the time for go through 1 or 2 more charts before the break, or
That's fine.
okay.
Whatever's good stuff.
I'll go through the state estimator and then we can take a short break. The state estimator, again, we were only getting attitude information at 6 1/4 hertz from the primary thrusters, trying to maintain an estimate of the vehicle rotation rates. We also wanted to know what disturbances. On orbit, you can have outgassing of the vehicle, you have gravity gradients, you have aeroturks, which have a diurnal variation depending on where you are in Earth orbit relative to where the sun is, which are tending to torque the vehicle in a particular direction. Having knowledge of how that the torque is behaving at a certain time enables you to manipulate your phase plane switching lines to more efficiently use the jet. So we were trying to estimate that. Given that we only had IMU data with noise and quantization effects, we also had flexure we weren't accounting for in doing that. So we had a low rate filter, which incorporated the measurements directly, and a higher rate filter, which was also taking in feed-forward information. We're going to fire the jets. We say, we expect these velocity changes, rotational and translational, to occur as a result of the jet firing, and you can build that into the estimate to anticipate that effect. And then, given all that information, basically use that in the form of a common filter. We had different gains associated with primary and vernier jet usage because these were given the factor 30 difference in the rotational acceleration authority of these jets. They were fundamentally different bandwidth systems on the basis of the actuators. So we accommodated those different bandwidths in the software. That, by the way, affected us when we started worrying about flexure on the arm, because we found that some of the modes with heavy payloads in the arm actually fell within this bandwidth, and were, in the case of the vernier jets, were falling right near the roll-off point, which is the worst possible place to have a flexure mode. And there were some significant design issues that were addressed later in the program as a result of that. And then this disturbance acceleration.
At the time that you were designing these, did you have was there sufficient knowledge of the structural modes and the bending modes?
For the RMS payload operations, not at all. We first learned about that when we started looking at use of the ARM to deploy the SPOS-1 payload in STS-7. Nobody understood at the time we were designing for the first shuttle flight the kind of coupling effects you would get from payloads on the ARM. It hadn't been modeled yet. I would say probably about the time the first flights were occurring is when we were starting to look at that stuff. But the shuttle software for the first flight was 95% frozen by 78, even though the flight didn't occur until 81.
You then discovered them in simulations or from flight data?
No, it was from high-fidelity simulations with the ARM dynamics included in this. We understood it pretty well. We refined it after the flights, but I don't think there were any big. We even did some flight tests on STS-8 with an object called the Payload Flight Test Article. The original payload on that flight couldn't fly in time, so they put this 8,000-pound dumbbell on there, and the arm was able to manipulate, went through all kinds of exercises. It pretty much validated what the simulations were telling us at that point in time. But it was a real lot of work that went into those high-fidelity robotic arm simulations and coupling that to the flight control system to get those numbers, and a lot of work into evaluating what it all meant in terms of the restrictions on the use of the control system. And then the last thing I'll talk about before the break, the disturbance acceleration estimator had a 56-second time constant. Most of these disturbances we're talking about were either orbital or semi-orbit, half-orbit type of periodicity. So you wanted to allow adequate time to integrate and determine their effect, but not so long that you weren't able to properly respond to it. So somewhere in the 1 minute range seemed to be about right for something that would have 45-minute periodicity. And I think the next topic would be RCS processor, and that is a good point to take the break.
Let me just, before we break, let me ask just one historical question. The time frame for the design of this was mid to late 70s.
We began the work in 75. There was a famous phase of 76, which is the hay scrub, which is where we realized that not everything can go into one computer. The computer memory had to increase. So the real design architecture of what was going to be the first flight started to gel in 76. The original expected launch day of the shuttle was 78. Kind of stayed ahead of us a certain amount of time, but we had probably 90 or 95% of the design done by 78. We're going through detailed flight verification and crew training, with Jeff being one of the crew members that was assigned to us when we would go out to Downey to do that in the 78 to 80 period.
In the design, I mean, you referred to the state estimator and optimal control. Had by that time methodology be completely accepted as a substitute for the classical control design?
Oh yeah, I think so. I think the phase plane concept first appeared actually in Apollo, and that was sort of a rudimentary application of optimal control theory that was quite successful. By that time, I think the aircraft zoom maneuver and other work had fallen out of this. People were happy with that. The Kelman filter work, a form of that, an early form of that, also made it into Apollo. So I don't think we were actually pushing the envelope that much and using these things. We actually carried over. But Apollo, it was very applying any of these technologies in the mid to late 60s was very groundbreaking.
Any other questions before the break? Okay, let's take 5 minutes.
Sorry. We from Monday.
Am I missing anybody? I know Larry hasn't come back, but
Close enough.
close enough. Okay. Well, I'm going to go into the RCS processor now. We've talked a lot about the presence of the phase plane. We're going to go into some of the details and the jet selection. Important considerations with the jet selection is we had to accommodate failures, maintaining control authority for any type of single failure, thruster, manifold, string, which you'll see more of later. And you also had to be able to maintain adequate authority for safety with two of those combined failures. We also had to limit plume restrictions, accommodate the tank constraints that we talked about, having couples, not having couples, to balance propellant in tanks, to limit fuel usage when you didn't worry about translational coupling and minor orbital perturbations, and all those other special maneuvers that we pointed out before that required higher authority. You had your manual modes going in, and then you had all these steering modes, which were on orbit, in addition to the ones we talked about, discrete rate and pulse and accel and all that kind of stuff. You had various landmark tracking modes, orbital object tracking modes, which were a guidance function providing inputs to the control loop. That all had to be managed through a proper way of manipulating the phase planes so they were tracking the errors that mattered with respect to the mode that you're in, and then sending, based on the errors being detected in the phase plane, commands that would be processed by the jet selection logic. So the principles of the phase plane. We figured you weren't important enough to get started. You had a phase plane per axis, roll, pitch, yaw. You had switch lines which were shaped based on the expected torques. Always had a parabolic feature, but much more complicated than just that. You added deadbands because you didn't want to fire when you didn't know exactly where you were. You wanted to be able to get in the general vicinity far enough from a firing zone that you would stay in that general vicinity for a while and then only fire when you had to, when you were diverging from that. You had to deal in the transition phase with that rate gyro noise phenomenology, and you had to get the disturbance acceleration on orbit. What we did about all those maneuver modes is each phase plane had an origin, the origin being 0 with respect to sun frame and attitude and position. You could move that origin at a rate, or you could increment its attitude position if you were commanding the vehicle to do something, such as a tracking maneuver or a discrete rate. And that way, the errors that the phase plane were looking at with respect to where you wanted to be rather than in an absolute sense. And you would always create coast zones in here so that if you had a big error, you could spend a little bit of fuel to get to somewhere which would cause you to go in the right direction without continuously firing the jet. Whereas if you truly followed the parabolic switch curve, you would just keep firing the jet until you were back to the origin, which could be quite costly. So I'm going to show you this picture and then the on-orbit one. These are the residual of the parabolic switch lines, which in the optimal control theory would be going through the origin. And then if you're out over in these regions out here, you will always fire a jet, F meaning in the plus direction or the minus direction. You're inside of here, you will fire until you hit another switch line on the other side. The expectation is that you're coming in this way or you're coming in this way. You want to get to a point where you're not likely to fire again for a while. But then you also would be concerned that if you fired and got over here, you don't automatically want to fire back right away because the rate gyro noise phenomenology could cause where you think you are with respect to that line to move back and forth, causing you to fire too soon, causing you to fire again to reverse that and get in trouble. So what we actually did is if you actually hit this line and began to fire, we would, each time you fired up to 2 or 3 times, you would move the line out so it would be temporarily so that the quanta noise from that MDM would not make you think, even though you were moving this way, that you'd gone back out, keeping you Because if you fired that jet again, not only would you be spending the propellant to go in there faster, you hit the other line a lot faster still. So for every time you double the amount of time, double the size of the impulse that you use to reverse your rate, you're quadrupling the total propellant time, because you double the propellant at each time you hit a surface, and twice as fast before you get to the next one. Now on orbit, we didn't have that noise problem, so we don't have that moving switch line there, but we have this moving switch line. If you're coming in, you're looking to hit the 0 line and cut off, but not really here. You're not going to cut off until you hit the disturbance acceleration line, but it's expecting when you hit that, the predicted accelerations are going to say going to go up this way. That means it'll be longer before you hit another surface than if you start doing that over here. So this was a trick to lower the frequency of the jet firings based on other knowledge that we had about the acceleration. Jet selection, we had entirely different laws for the primary and the verniers. The verniers had the very complicated configuration, had to be able to get be fault tolerant, be able to handle simultaneous translation rotation commands. It turned out, because of throughput processing limits, the correct approach was something like a table lookup, but we had all kinds of rules we went through to say which kind of table do we want to go to? What are the consequences of failures? Do we want to start modifying the commands we've received because of what we basically know about which jets have failed and what we no longer can accomplish? We actually had a Boolean implementation of those tables. It actually got implemented as tables, though, because we developed algorithms and IBM converted the software, and they didn't necessarily do exactly what we told them. Subsequent to that, there was an experiment on the shuttle. It's called a phase space autopilot, which is looking at based on looking for velocity changes and optimal combinations of jets. You would go through a linear optimal search and find the combinations. That was flown a couple times for a few hours on shuttles. The experiment was quite successful, but never converted into a basic shuttle capability, but certainly with the processing capability that you have now would be a very good option as an alternative to what we did. The vernier jets, which were only used on orbit, only had 6 jets. We weren't trying to deal with redundancy, so an entirely different kind of scheme was done there. We were looking to find the jets with respect to a 3-axis command which best contributed to producing rates in that direction. We could find a first jet that would be the best jet, and then we could see, given how good that one is there another one which is half as good? If so, we would pick it. And if we found one that's half as good, we might say if there's another one which is half again as good, we might pick that and end up with an aggregate number of jets we would turn on to start producing the command. Then, this would be based not just on whether or not the phase plane said you should have a jet fire in an axis, but also on how far you were, how big the error was, but not yet to the point of hitting a phase plane line in the other axes. And so the composite vector you were trying to neutralize would be a combination of the command and error reduction in the other axes, and you would find the jets which would then respond to your command and reduce the errors in the other axes. Now, we would not recompute that every cycle. If we found that the ones or minus ones in the 3 axes for the commands were not changing, even though the fractional values in the uncommanded axes were changing, for up to 5 cycles we would not recompute the jets. And that would minimize the duty cycles, which was a life issue on the jets. And then there was the other phenomenology I mentioned, which is you start having large payloads, or you're attached to mirror or something like that. Mass properties are very different. We don't know about that unless the crew tells us, but we could put a discrete number of alternative configurations in the tables for what the expected accelerations of the jets would be. The crew could tell us which one applies, and then it would do this selection based on that. So the vernier algorithm looks something like this flowchart, whereas the primary algorithm would probably fill a 50-page flowchart. The vernier algorithm was very simple. You go through, you have a command vector, which was ones and minus ones or fractional values, depending on whether the phase planes had commanded an axis or just had a bias because of an error in that axis. You would do a dot product of the 6 jets. You would look for the maximum value of that dot product of the acceleration and the command. And then based on the value of that dot product, you'd see if there was one that was half as good, and if there was one that's half as good, you would see if there was one that was a quarter as good. And then if we had already selected, we would be doing this counter of up to 5 times where we wouldn't recompute. Now, I was just talking during the break about one of the constraints on here is when we were using these computers, a dot product of a 3 vector by a 3 vector took about 1 millisecond. We had an 80 millisecond cycle, and in that 80 millisecond cycle, 7 to 10 milliseconds could be allocated to control. Some to nav, some to guidance, and some to other functions. 6 milliseconds was being used to do these dot products. That's why we never could have considered doing something like that for the primary jets. The TVC processor, we have, instead of discrete control with thrusters, we have nearly continuous control because we're doing gimbal steering up to the nonlinear effect of a gimbal limit.
Remind them what TVC is.
Thrust vector control. Moving the thrust of the OMS engine by steering the gimbals on which it's attached, which you can't do with the RCS thrusters. What we would do then is cross-product steering was you have an error vector and a thrust vector, and the cross-product between the two could tell you the direction you needed to steer the vehicle to turn into the desired direction you wanted to thrust. That steering command was then used to determine the commands we sent to the gimbals for moving the engines. You had a manual and automatic modes for doing that. Generally, we were limited to 2 degrees per second because the gimbals were fairly slow. We didn't want to get ourselves in a situation where we oversteered and had to correct back, which would take a lot of time and maybe cost us some propellant. But if we got into trouble, the reaction control system could wrap around, and that could happen automatically if the errors got big enough, or the crew could induce that by hitting the hand controller. And you have the 2 paths going into the manual or the automotive. Manual always override auto from any of these operations. We had a lot of things we had to tolerate in determining our filter gains. We didn't always know the thrust direction of the engines all that well because there's mechanical misalignment. When you build this thing, an additional misalignment occurs after you launch the thing, causing changes in the gimbal drive connections a little bit. There's errors in the you rotate to a desired burn direction with the RCS jets before you light the engines. You're never exactly there when you start up. You can have failures during burns. An engine can shut down, an actuator can stop driving, and you can, if it's the OMS 1 burn in the early shuttle days, during that burn they were dumping the residual oxygen and hydrogen in the feed lines for the main engines during the burn, causing a torque disturbance on the vehicle that we had to overcome. The OMS burn actually helped drive that fluid out of those lines. And then, of course, we had sensor noise and bias. And then we had to have margins for things that all liquid propellant vehicles have, slosh, flexure, actuator nonlinearities, and sample rate effects. Now, we had a design, and then we had to change it. And the reason we had to change it is we flew for a little while, and we discovered that these brushless electric motors being used for the OMS actuators were turning on and off at a high enough rate during the burns that they were overheating, making the 100-mission life maybe 2 or 3 missions. And they were also fairly hard. They could take the pods off, but they were fairly hard to get and expensive to maintain. So they asked us to change the bandwidth, and that's what we did beginning with the 12th shuttle flight, making these changes here. And that caused a little bit more sloppy behavior at the beginning and end of the burn, but didn't make very appreciable difference on the performance and made a big difference on the actuator life. There was an outer loop just showing where the cross-product steering comes in and the fact that there are various filters and digital compensation effects that are going into this to deal in an adequate manner with all those effects that I listed a few minutes ago. The wraparound was there because we have the means to cover for large perturbations. Why not implement it? I mean, the situation you always have with human spaceflight, if there's a capability you can take advantage of in a contingency scenario, put it in. This also changed, though, between the first flight and the 12th flight. And the reason we found is that you put this contingency capability in, but when you really study it, you realize you can actually take these two fundamentally different control laws and cause them to interact adversely. We could perturb it and then induce the jets to fire in a way that would cause it to counteract the effect that the thrust vector control system is doing. So when we lowered the bandwidth, we also changed some of the parameters in there to, in combination, preclude that force field. So this is a case where we continued to evaluate the baseline system after we were flying and discovered additional potential unanticipated deficiencies that we should fix. Which is saying you're never done analyzing a system even after it starts flying. The maneuver and track modes, I mentioned that they were there, but we had this universal pointing display that the crew could manipulate to draw. Yes?
On that last general comment, on the last subject of discovering issues and potential problems after the system is flying. You're doing it. You're doing the analysis. You do your research. What in general was the reactions of your NASA counterparts when you bring that to their attention? Would they call for an immediate fix on the next before
on the
the next
nature
launch?
Of the problem. And let me mention 2 or 3 of them at one time. This one, I mentioned the one about that phenomenology for the excitation of the rocky motion on the tank, and then another one with the vernier jets, which I'll explain in a moment. The external tank one had to be fixed before second shuttle flight. That was one that potentially created a dangerous situation, tank separation, violated safety of flight rules. This one, this potential wraparound interaction, could only occur if you already had a significant contingency under fairly complex conditions, and if the crew knew about it, there was a procedural way to temporarily inhibit the reaction control system interaction, stopping the effect. So because it was a crew workaround, they knew about the problem, it was deemed acceptable to go some number of missions for an already scheduled software update to insert it. Now, the third problem, discovered as a result of analysis of STS 1 and 3, was a plume impingement phenomenology of the downfiring aft jets. The body flap sticks out as in kind of a random position on orbit, and the downfiring thrusters, part of their plume hits it. They had evaluated that effect for the primary jets because they knew in the direction they pointed in their lower expansion ratio than the vernier jets, there was going to be a problem, and that was properly dealt with in the flight control system. But they never modeled for the vernier jets, but only discovered that the state estimator was not converging as well as expected on the first shuttle flight when using the vernier jets, and it turned out there was probably a 20 or 30% net reduction in thrust and a 15 or 20 degree effective change in the direction of the thrust, those two downfiring verniers. And the feed-forward estimation from the RCS jets as a result was giving the wrong data into the state estimator, causing a jump in the value and a long time constant to settle out, and that was causing a factor, a few percent increase in the propellant consumption, but probably a factor of 10 increase in the duty cycles of the jets, which was unacceptable from the life of the jets. That was compounded by a problem on STS-3, which was the first time they used the arm, and they actually put a few hundred-pound payload and tried controlling the attitude of the vehicle while moving that payload. The combination of those things meant they went back to, by STS-5, had to make a series of changes to the phase plane and estimation logic and tables for the accelerations for those vernier jets, because they didn't want to burn those jets out. I think actually after STS-2 they actually changed some of the jets, and then they didn't want to have to change them again. the maneuver mode, I mean, you want to do various type of eigenmaneuvers with respect to various frames of reference, which could be landmark tracking, local vertical tracking, second spacecraft if you're doing a rendezvous tracking. Guidance would provide that. That would be broken down into components by axis. And then there was an additional level of hysteresis about what you were telling the faceplane to do. I talked about adjusting the origin. This would decide whether or not you would adjust the origin. If your error in a given axis with respect to what you wanted to do with the maneuver was less than twice the deadband, you would not adjust the origin. And if it was more than twice, you would. And again, it's a case of why force it to do things it doesn't have to do if it's going to get there eventually anyway. And that's actually an adjustable parameter, which for certain payload missions they might change that value from something else. There were these various direct manual translation rotation modes and the auto modes. I think bit by bit I've talked about, but the reason you have these different references, inertial and local vertical, if you're doing a Earth observation mission, almost everything's going to be in a local vertical frame. You're going to have your payload bay pointing down. You want to keep it pointed at a certain spot. If you're doing a solar telescope mission, everything's going to be in an inertial frame. You're going to want to keep it pointing at the sun, or within a few degrees, where maybe the telescope will have a limited travel of its own. If you're doing rendezvous, then it's going to have to be with this, accounting for the orb rates of the two vehicles. You're going to want to keep your rendezvous radar pointed in the right direction. By the way, the rendezvous radar, there's a deployable dish antenna that goes out of the payload bay, side of the payload bay of the shuttle. That's a dual purpose antenna. It can be used to point at the TDRS satellite to send data at high rates to the Earth and track the satellite, or it can be used to point a radar beam at another spacecraft. It was not used for TDRS. In the beginning of the program, it was only used for radar because the first TDRS was launched by STS-6. Electronic stringing. I think we're about at the right point of time on this, too, to allow me to get into this in a little bit of detail. This was something that kind of crept up on us in importance. There was thought in make the systems redundant, have separate strings, don't put them all on the same computer. All those things were recognized. But I don't think until about a year and a half before the first flight actually occurred do we realize how difficult it is to be sure that all the interactions of these strings, the power string, the plumbing string, and the electronic string, and the possible combinations of failures, how difficult it is to assure that you meet those high-level failure tolerance requirements. And that's where I think what I did in 1980-81 probably was the early form of fault tree analysis. And I have in a handbook I developed for the first flight a series what-if tables with all these different breakdowns of what could happen. And it was actually a person that didn't know about probabilities and all looked at it. It was a pretty scary table when you looked at all the possible bizarre two-failure combinations. But first you got to understand what the strings are. You would have one forward, one aft, and one aft left and one right left with right aft, so 3 boxes, 3 half boxes, and multiplexes, demultiplexes per on a string. And the reason I'm talking about, there were 2 MDM boxes in each pod, forward, left, right, aft. And the electronics were broken apart into each half box. So you actually had, in effect, 4 sets of electronics in each pod, even though you only had 2 boxes. And 1 card from each of those boxes would be dedicated to string, but each string would have a card per pod. So 3 cards, would be tied electronically to one computer nominally. Now, you couldn't take a string that could be commanded by more than one computer. The computers saw the data from all 4 strings, so they could vote the data to decide whether or not each of the computers was healthy, but they could only command one string. Or I should say each string could only be commanded by one computer, but you could, if you started losing computers, latch up more than one string to one computer. So even though one string could only take commands from one computer, more than one string could take commands from the same computer if that became necessary. So if you lost a computer and were in a benign environment and you wanted to recover all those systems, that's happened with the first computer failure on STS-9, then you would manually relatch those strings to a healthy computer. Of course, if that computer went down, then it would take 2 strings down. There was a unique lash-up of these strings components to power systems, but it wasn't necessarily one-to-one, and that's where things got very complicated. When you start crossing the subsystems where one power system could cause some subsystems to fail on more than one string, then you take a string down, that'd be a very different failure scenario than taking 2 strings down. This is showing how the thrusters laid out. You can see there's a lot of thrusters on each string. If you go back and look at the vehicle carefully, and you look at the down-firing thrusters, you'll see that in the front of the tank there's 2 thrusters that point down and to the left, and 2 thrusters that point down and to the right, canted out about 40 degrees. That means that if you lose 2 thrusters, 2 strings, or 2 manifolds, it is possible to lose both of them on one side. That's very important because that's one of the phenomena we had to protect against for separating from the external tank, and it becomes a highly coupled separation maneuver. And there were some special jet select tables that created from that, and some special control logic loops that were created just for that one scenario. You go through these things and you have certain critical events where things cannot fail, even if your subsystems have failed twice. And the subsystems may not have been designed to make it very convenient, but you still have to do it. So that happens to be one of the scenarios we looked at a lot. And that's, we see down, forward, down, left, or forward, down, right. So somehow you lose these thrusters, these strings, or whatever. That became a special design case. And there's a lot of those kind of things that I would say 70 or 80% of our design time goes into worrying those special cases. With the ohms, you not only, with the thrusters, the manifolds are basically the valve lines, so there's a commonality between the electronic stringing of manifolds and the valving. With the ohms, that's not really true. You have these, the way the ohms engines work, each engine fed from is actually an oxidizer and fuel tank going into 2 loops of lines, each with 2 valves. At least one valve in each path had to open to feed fuel. At least both valves in one loop had to close to stop fuel from flowing. So any combination which would leave 2 open after burn started, or would leave 2 closed before the burn started, was a problem. Then you have pressure sensors, and there was only 1 per engine. So you lacked insight into whether or not the engine started based on pressure if one of those failed. The stringing of this was not the same as the electronic stringing. So we had to start looking at the possibility of individual valve failures and electronic string failures, taking down other valves. Did that happen before an engine started, after an engine started? How did that correlate with the influence on the same engine's actuator control? So we could get situations where we could start the engine, but we couldn't steer it. At engines where we could steer it, we couldn't start it. And so we ended up with this maze of tables. Look at those situations, coming up with contingency design, sometimes reverting to using the XRCS jets under severe multiple failure scenarios to actually do deorbit burns. So we talked about what could go down. All of these things could be lost with a single failure, though not all strings had an IMU because there are only 3 and only 2 of the chamber pressures. So some strings were more important than others with respect to a subset of the systems. Since there are only 2 thrusters on 1 manifold per pot of the verniers, there are also only 3 strings that affected those. But all this got set up so that any one failure was quite manageable. But the moment you talked about any possible 2 failures is when it became much more complicated. So generally, where we ended up after lots and lots of special design accommodation was we tolerated loss of translation control in the axes that were not necessary for managing deorbit. We tolerated degradation of rotation control, but assured that we retained it at least in a time average sense in all 3 axes. The biggest complexity here was assuring we still had adequate time average translation and rotation control for tank separation. So we would pull away without recontacting the tank. Remember, recontacting the tank meant tiles hitting the tank. Those tiles are really fragile. They can survive thousands of degrees, but not much impact. We accommodated the scenario where we could lose all thrust vector control in the Ohms engine and still do a deorbit burn, usually with RCS wraparound properly designed. And we had to accommodate the situations where MDMs did not reset, so everything tied to an MDM would be lost. And that's the kind of situation where you start having valve here, valve here, valve there being shut down along with a bunch of jets. And the real pain was understanding what things could collectively go down together, coming up with so you had to lay out all the faults, all the things that could happen with each of the faults, and then overlaying the combinations of those. And then you would find, it wasn't everything you were worried about. It was usually a small fraction, but those few fractions drove the design details and effort to a great degree. Now on orbit, because you would often be using one IMU and you only had 2 computers, one of those strings going down meant you lost your navigation base. But because you're in a relatively benign environment, restringing, bringing up another system wasn't a problem. If you were doing terminal rendezvous with the space station, you would not be in a 1 IMU mode, you'd be in a 3 IMU mode on 2 computers. But you would not lose your navigation base. If you lost a computer at a critical point in that, you'd probably abort the rendezvous, reconfigure again, and resume your operations. One of the ground rules for all rendezvous operations with the shuttle, and I think will be true of the CV, is any rendezvous operation you plan to do has to be able to be repeated at least once. So what I wanted to end this, and then we can have questions, is 2 pictures, before and after cockpit upgrade on the shuttle. This was the way the shuttle was for many flights. Those are CRT displays, monochrome, green monochrome, where no images could be drawn except little sticks, dots and lines and rudimentary. These are analog tape measures, analog 8-ball with analog needles for attitude and rate information. And really very 1970s.
Comment on that. One of the things that we did as payload specialists is we got some training in the cockpit, and that was the version that was available in the early 90s when I was down there. And you'd go from your desk at the Johnson Space Center when you were using a IBM ThinkPad or something, and you felt as though you'd gone through a time warp when you went back to the simulator on what was the world's most expensive vehicle. It was extraordinary, and of course you could explain why this was kept on so long.
Well, it was the multi-7-digit figure for its upgrade, as well as the issue about recertification. So, and let me mention both of those in a moment. Point out a couple of things and then get back to that before I show you the current configuration.
What was the million line of code? How many the software, the total software of the shuttle?
Well, the amount in the shuttle versus the amount to support the shuttle are
in the shuttle, because talk about certification.
Well, you only have the 104K memory computer, so you have the actual number of lines that are.
Yeah, but you have overlays.
You had the 104K for the backup system, the 104K for asset and entry, the 104K for on orbit, the 104K for SM, system management, and then there's been other things with their own software capabilities have been added in subsequent years. So it is a lot of software now, but human validation means you make small changes and everything has to be reassessed for possible interaction to a degree that you would never do for a mission that doesn't put human safety at risk. And that means the cost of doing that each time is probably an order of magnitude higher than it would be for an unmanned system. So you look at what it was going to take to put a cockpit upgrade in there. We're talking hundreds of millions of dollars to do it for the fleet. When I say hundreds of millions, a couple hundred million. It did eventually get done, as I'll show you in the next picture, but the main reason was obsolescence rather than wanting to be contemporary. You can't buy these pieces to replace them anymore. You can't buy, the companies that actually made some of these systems may not exist. Or if they do, they have no economic incentive for maintaining a base for a customer that may buy another 5 of them. And so one of the things you have to deal with a system that's going to go this many years, another example of that is the B-52, is you have to, or the Trident missiles or things that stay in operation for a long time, is you have to plan as part of your operation cost for periodic upgrades to mitigate obsolescence.
Well, other things they do, they buy all, they predict how many instruments will fail, and they buy them a priori so they have in stock.
Well, we had, I remember for some program, we had in some program they had some support. It was digital microcomputers where we had a room over in the Hill building that had about 100 of them stacked up as backups. I don't think the boxes ever got opened because I think the program did the buy, but the program never lasted as long as it was supposed to. But you are right. You can try to buy it, but even so, even unused systems have a shelf life. You don't know how good they're going to be 30 years later. If you had asked me in 1978 how long the shuttle was going to fly before it was replaced, I would have said 10 years, maybe 15. Before the Columbia accident, they were talking about another 20. It's only the safety issues now that are going to make them stop it sooner. Anyway, the other things I want to point here, this is the crew interaction mechanism, a push-button display. No such thing as GUIs. That's unheard of in the shuttle.
Can you talk a bit about the hand controllers? Are they the same ones used for if you're landing that are also used for docking? Is it the same hand controller for everything?
It is the same hand controller for everything, except there's another station in the back. I didn't bring a picture of it, which is used for docking. The cockpit, you're looking out the forward windows. You turn around, there's another set of cockpit instrumentation hand controllers, and there's 2 windows above you and 2 windows looking on the payload bay. So and there's also controllers there for the arm. Everything related to the arm is down looking out toward the payload bay. The arm's attached there. When you're doing rendezvous, you're looking out at the overhead windows at the vehicle you're approaching. So in effect, you have a couple of these CRT displays and identical hand controller and the equivalent then or the updated equivalent now of these displays on a back station.
To avoid any issues of changing controllers and changing viewpoints, you might note that normally the controls that are done out the back window with that separate controller and separate displays are done by different crew members. That's typically a mission specialist.
That's right.
Mission specialist job, not a pilot or commander job. And so they're separately trained.
Right. Right.
But
Important point.
For rendezvous and docking, it's the pilot or commander who uses the aft controls to look out, to control it.
Do you know?
I believe that is everything related to the RMS, which you said is correct. But for rendezvous, commander's always involved, and that.
Point was that in that case, that's done out the rear window.
It's still done out the rear window, so he's got to mentally reverse his frame of reference while he's doing that. That is correct, and it's not a.
Yeah, that's right.
So that is something that I think will not be done with the CEV. It's the same frame of reference will be used on the CEV, because I think that's always been a little bit of a point of contention in the problems of maintaining simultaneous proficiency.
For remote manipulation with the arm, that has been an issue.
Yeah, and I think that has always been done by a uniquely trained mission specialist.
Right.
That's right. Today's cockpit looks a lot more like what you'll see on a commercial airliner. Vintage mid-'80s to late 80s, perhaps, but still more familiar, where you've got glass, multicolor displays. The 8-ball still exists in image form, because that's what a lot of the astronauts use to learn how to fly this vehicle, so they still fly with respect to it, except it's a digital representation. But you still have the same push. You're still not with the GUI environment. You still don't have touch pads or mouses. It's all push-button displays. And there's a case to be made that touch displays or touch screens don't work very well in a vehicle where your G environments keep changing. It's very difficult to get a touch display that works with a light touch and a heavy touch, so when you're in 0G or when you're pulling several Gs. So even if the technology were space qualified, it's not clear that they would use it except on a vehicle that stays in a constant environment.
So at this point, let me introduce Dr. Hawashi. Miwa Hawashi is, in fact, at NASA Ames Research Center now, was here at MIT, and worked on the design of the next generation of the shuttle cockpit upgrade. In fact, that's what you will be talking about in 10 minutes across the hall in the 16400 class.
Essentially, what would have been done if shuttle life had been extended.
Right. I might add that although the room is very crowded, if a few of you would like to sort of hear where this story would have gone, you're welcome to come across the hall to 419 and hear Dr. Hawashi. And you're also giving a lecture, a lab meeting lecture at 1 o'clock. Could you tell us that subject while I interrupt?
That's about the astronauts scanning behavior. Our team had a model about the astronauts scanning the behavior in a MEDS cockpit. This one, upgraded cockpit. So anyone interested in this kind of topic, very welcome. It's from 1 p.m. 33-206.
Thank you. Go ahead, Phil.
Well, at this point, I think I'm open to a few more questions.
We have a couple of minutes for further questions. Thank you, Phil.
Any topic we've covered or that's related that we didn't cover. Yeah.
I guess you talked a lot about the constraints of the embedded computers and the way it limited you, but how did you verify and validate this before the first flight? And how you were limited by what you had in your lab as well in terms of doing the simulation?
Well, we had very large facilities for that purpose that evolved over time. The first major facility was the Flight Simulation Laboratory in Downey, California, which was then Rockwell. You had a room with a couple cockpits. You had another room which had the digital interfaces to the cockpit, and half a floor, which were the analog computers that provided a lot of the information generation at a rate that was not achievable with digital systems. So you had this hybrid system for driving what were man-in-the-loop simulations, and we spent 24 hours a day, 7 days a week using those labs for several years. I would often go out to California and be on the 5 p.m. to 5 a.m. shift, often spanning weekends. By the way, I was doing that, I think, when I was still a graduate student, which was kind of an interesting experience. Then NASA built the Shuttle Avionics Integration Laboratory in Houston, which eventually superseded the laboratory at Rockwell. That became an all-digital system. The hybrid systems went away. The high-capacity computers, you could fit in one good-sized room everything they needed, and were able to get much more digital displays for the crews. Sometimes what they used to do for the imagery the crews saw in the early days is you would actually drive a camera across a simulated scene because you couldn't generate the scene. By the time they got the sail facility developed, they were able to do scene generation with fairly high-capacity computers. Now everything is, could almost be tabletop. I mean, it's so dramatic as how this evolved over the years. The one thing they had at Rockwell that never got replaced, though, is they also were able to put into the loop actual hydraulic systems. You would hear this when they were doing entry. They could turn on aero surfaces and hydraulics with simulated loads, and it was you always knew when they were doing it because the high-pitched scream of the APUs running when they were doing it was you could hear it 2 blocks away.
Okay. The last question.
Sir, I was wondering if you could give us kind of a concept of the cost of developing the software, either in man hours or, in comparison to what they spend on the hardware.
Well, the initial development of the system probably involved the equivalent of 15 or 20 full-time people for a few years. And this was to develop the algorithms and support the validation. The actual flight software was actually produced by IBM separately, and they had a small team of people that would take the detailed design specifications and they would create the software, and then we would get back in and validate the software. And I would say a big chunk of that effort went into accommodating the many constraints we talked about. The team didn't go away at that time because then we started getting into capability extensions, applications to payload operations. The team shrunk, but didn't go away. It's a big effort, but a very small part of the cost of developing a shuttle. I mean, you measure the shuttle in billions, you measure the flight software development in millions.
One thing that I remember when the software was developed and we were working and validating it, IBM wanted for every line of code change $1 million. $1 million for one line of code change because they had to verify the whole software.
Yes, that's why you would never.
To make sure.
That's why you would never, unless it was a flight critical thing, do that. NASA wanted generally, whenever possible, to aggregate changes for a year. Or maybe 2 years sometimes, and then put them in there just for that reason, because there was this huge cost of revalidating, and that was the IBM cost. It would be a cost to bringing us back in to certify that too.
Well, it worked, and you should be very proud of it, you and your colleagues. Thank you very much, Phil.